Chapter 2 is on functions and relations and graphing those and other aspects of functions mostly. 2.1 is on the rectangular coordinate system and graphs. So this should be review, getting into what the rectangular coordinate system is, what it looks like. So go ahead and draw your graph and label. What you normally do is label the positive direction with the arrows. You may label both sides like that, but normally you do your line and you do your positive direction with the arrows. That's kind of typical how you draw it on your paper at least. And then you label the axis. Sometimes it's t, sometimes it's different variables, but usually we say it's x and y. And then we have our quadrants. Going upper right quadrant, that's quadrant 1, and we usually use Roman numerals. Quadrant 1, and you go counterclockwise. Quadrant 2, quadrant 3, and quadrant 4. That's how it's usually done. And we can talk about points in those quadrants because there's 4 of them. And so to describe a point, say here, then you count over 1, 2, 3, 4, and you go up 1, 2, 3, 4, say 5. How about that? So this would be the point 4, 5. So that's called an ordered pair. 4, 5, like that. And then if you go down, this would be negative. So this would be still 4, but then you're down negative 1, 2, 3. And over here, let's do a couple more. How about negative 1, negative 2, down 1, 2, 3. How about that? So that's negative 2, negative 3. You go say negative 1, 2, 3, 4, 5, and then up 1, 2, 3, 4. How about that one? So now we have points in every quadrant just to describe it. This would be 5 here. Oops, did I count wrong? 1, 2, 3, 4, 5. So that was, how about negative 4, negative 4? Positive 4. I wrote that wrong. So negative 4 along the x, and then 4 along the y. The value, as I mentioned, x, y, is called an ordered pair. And usually it's referred to as, this is the horizontal and this is the vertical, is the way it's described. We can describe the distance. I want to show you how you would derive the distance between 2 points. So you may know the distance formula or seen the distance formula, but let me show you how you derive it. So I'm going to make it off over here. So suppose you have this point, say here. We'll call that point x1, and we'll call this point y1. So it's x1, y1, and then we'll do over here, say x2, and we'll go up to right about here. We'll call that y2. And so we are getting these points. We call this point, say, P, which is x1, y1. And this point over here, we'll call that point Q, and which is x2, y2. So we're doing this in general, generic, for any values. And let's suppose we want to find the distance between those 2 points. This distance here, like that. So what is D? What's that value D? A couple things to note. That has to be positive when we derive this. Kind of obvious that it does, but it has to be positive. Let's see. Let's do this dotted. So what you look at or use is a right triangle. So you look at this right triangle. And does anyone know what formula you may want to, what you use for this formula? And some of you are correct. It's the Pythagorean theorem. You basically use Pythagorean theorem in the end here. So what you want to do is figure out this distance and this distance. So this is like A, B, and then we'll say it's D for distance, but it could be like a C, and then you use Pythagorean theorem. But with them being ordered pairs, what we do is we look at absolute value, because we don't care which value is positive or negative, so we'll always get distance if you do absolute value of x2 minus x1. So that order doesn't matter when you do it this way. And then similarly, this will be y2 minus y1. And this is like your A, and this is like your B. And then when we square these, you square your A and your B in your Pythagorean theorem, you can drop those absolute values. So what you use then is that D squared is equal to A squared plus B squared. That's the Pythagorean theorem. And so D squared is equal to absolute value of x2 minus x1 squared plus absolute value of y2 minus y1 squared. But you're squaring absolute values, so you can drop those. So D squared is equal to just x2 minus x1 squared plus y2 minus y1 squared. And it doesn't matter the order of those values, right? Because you're going to square it anyway. Then you take the positive square root and you get your distance formula. So this, and normally when you do this, when you solve for D, you say plus or minus. But because it's distance, we are going to use just the plus. I think that's kind of important. Okay, so x2 minus x1 squared plus y2 minus y1 squared, like that. So that's how you get your distance formula. And I do that, I like to do that one just to show you how these formulas, these concepts, they don't just pop out of nowhere, right? They're derived from some other basic facts, and then you can construct things that you want. That's how all math is done. All right, let's continue. Do just a quick example here using the distance formula. So, and this is when I like you to try stuff. I won't like pause the video. You're gonna have to have the discipline to pause it yourself. And just when I say okay, try it, then you can then pause and then work on it and then look at it later. So, here's an example. Find the distance between the 2 points -1, 4 and 3, -6, like that. All right, so try it. I mean, this is pretty simple at this stage. We're just going to substitute these values into here. And so what I do, so go ahead and try it. And then, okay, now you've tried it. Now I'm going to come back and show you how I would set it up. What I like to do is I like to label them. I like to label them like below or above. Say this is x1, this is y1. And it doesn't matter the order, x2, y2. It just has to be an x comma y is the critical part. And then so now, because I remember, I mean, it wouldn't matter because I could have switched the order, right? So and how I gave those to you. So I just wrote them down like that from probably the book. So it doesn't matter the order that you write those, but the y part does. The x and y part matter. But which ones 1 and 2 do not matter. So now substitute into your distance formula. We say distance is equal to the square root of, and now be careful of your signs. That's the biggest mistake people would make. And so it's going to be your 3 minus -1, which becomes plus, of course, quantity squared. Plus, and I always leave that short right there, so just go in and fix that. I will notice that. Make sure you go across. Okay, and then the next will be your -6 minus 4, which of course add, and that's squared. And I'm kind of picky when I write stuff, so I'm going to erase this little tail here. All right, so now simplify that. And you should get, this is equal to the square root of. Notice how I'm using equal signs. So you don't just write stuff, you connect with equal signs. And I'll describe that as we go. And so this is 4 squared plus, and that becomes a -10 squared. So the sign doesn't really matter, right? I mean, it's just going to be positive. So that's the square root of 16 and then plus 100. So that's equal to the square root of 116. And that's okay, but that's not good enough. We want to go ahead and simplify this down to an exact form. So that is the square root of, and this would take some trial and error. You could just start dividing by 2, but that's actually 4 times 29. And so you can take out that perfect square, which is a 2. So it's 2 root 29. And that's the exact form we want right there. Okay, so this right here is our exact form, and this is what we want. We call that exact. And that's what I'm looking for right there. Now, you may get an approximation using a calculator and stuff. And I want you do want to do that, is use a calculator to figure things out. So with a calculator, you type in 29, then you hit the square root button, and you say times 2. Usually that's how you would write it. And it ends up being 10.77032.961. And that's, again, that is just an approximation. It is not exact. Okay, let's see where we're at. Let's do one more thing for this video. So moving on, we're going to do intersection and union of sets. Important thing we want to look at, and number line type stuff. Okay, so this is on intersection. And union of sets. So what I want you to do is draw, we're going to start by doing a Venn diagram. So draw a circle. Oh, and I forgot to mention back here, I can draw it real nicely. They've upgraded this over the last few years, so I can duplicate and draw it like that. And I'm actually going to do this too, because I want you to do 2 of them. I'm going to duplicate that whole thing. So this is what I want you to draw, those 2 things right there. But back here, I almost forgot. You need a straight edge. So when you're drawing this, you don't have a nice, iPad like this. You use straight edge to do those. I always put that down in my syllabus. I use a stencil when I draw my circles on paper. I'm actually pretty good at doing it on the board. I can draw on the board pretty well, believe it or not. Anyway, I'm digressing. Okay, let's go do this. Okay, so I just moved that. I moved that back. I like how it helps me line it up. It's kind of cool. Anyway, so this is, we call this set A, and this is set B. So we say A and B, like that. Okay, so this is like the generic way to look at intersection and union of sets. So the intersection, we say A intersect B using that symbol. The way you describe that, and this is some of the notation we learned in the set lecture or video, X is an element of A intersect B. What that actually means is X is an element of A, and that's the key word there, X is an element of B. So what does that mean in terms of all of this? So this represents stuff that's just in A. This represents stuff that's just in B. And of course, the overlap means it's in both. So this overlap is the intersection. And you may have seen that before, but that's how it's described with what's called a Venn diagram. So that's the and concept. And then the other way is union. So we say A union B. And this is the or statement, and and we have to have that described for the or statement using the correct type of or. And I'll talk about that in a second. So X is an element of A union B means X is an element of A or X is an element of B. So that's what it means for X to be in the union. And often talk about this a bit in class, but the or is representing it can be in this one, can be in this one, or both. So what we think of this as, this is what we refer to as the inclusive or. We use the inclusive or statement. So the example I give for this is you're at a restaurant and you are asked if you want soup or salad with your meal. And in that case, it is implied what? It's implied you can have either or, but not both for that type of or statement. And that's called an exclusive or. Some restaurants, expensive one, you might get both, or you got to pay for it, whatever. But if you, after the meal, you are asked, and it isn't always phrased this way, but you can see what I'm going with this. If you were asked, would you like cream, like you have dessert, right? And they asked if you wanted coffee after your meal, and they asked, would you like cream or sugar with your coffee? What's implied with that statement? Well, it's implied you could have cream, sugar, or both, either or both. So that's what it means for the or statements, either or both. So it's all of that, all of this. Right, so it's all of one side, all of the other side, or both. So that's what we mean by or, the inclusive or. All right, so what does that mean for our notation? And so I want to describe when we describe this, it comes up whether it's a solution that has to be the intersection, or a solution it might end up being the union, and that comes up in our description of things as we go. Okay, let's talk about interval. So just hold on to this. We will come back to this concept and apply it to our actual stuff later. So let's look at interval notation. Interval notation is something that kind of all books like to do it from the beginning. It's not always the best way to describe it, but this is specifically for sets of real numbers. So it's specifically sets of real numbers. And breaking up the number line. So when we look at a number line or the set of reals, we think of just the number line like this. So here's our number line. And we think of positive infinity going off this direction, negative infinity going off this direction, and we often include 0 in the middle like that, like this. Okay. So when I break up the number line, and I will go ahead and duplicate this, you don't always put those infinity symbols like that. I'm going to actually erase them. My next example here. So that's how we usually look at the number line. And if we break up the number line, we can do this in a couple ways. So I'm going to do it this way first. Let's go down to, say, -1, 2, 3. So suppose we're here at -3, like this, and we're going this direction, like that, going like that. Then the notation, so that's a dot, or you could put a bracket at -3. Let me change back so you can read it. So -3. So it looks like this. So for including that, you use a bracket. Okay, so that's probably familiar to you. So you do -3, and then it's pointing towards infinity. So you say approaching infinity like that. And then you, of course, use a parenthesis. You never may include infinity. Okay, and then let's do another one. As we go here. So next one, let's suppose you start here at -3 and there's a circle around it, and then you have a dot over here. Let's say 5. I'm just making it up, the numbers, and then you connect. You want everything in between like this. So here's a circle, and here's a dot. So this means when it's a so that means include. This means not include. Right, so when you draw that in your interval notation, then it would mean not include -3, and then comma means everything in between all the way to 5, but we want to include it, so you have to bracket. All right, then the union notation comes up in this next one. It might look something like this. So if you have, say, I think I want to include that one. Yeah, so include, say, -1, and then not include 7, and then we're going opposite directions. We're going like this, like that. And I can make this look all nice, but I want it to look more like I'm drawing it on a pencil or something. Something like that. Then what we want, and we want to include both of those sets, then we use this union notation. We use this notation to say both. So this is, how would you draw that? Should we try that one? So you go -infinity all the way up to -1, bracket, and then union, not including 7, and then approaching infinity like that. So there's no real reason to use the intersection on these, because it ends up being just something like this, like it's what's in common to everything. But to use this as, like, these might be the solutions to some problem, you want to include everything that's written. That's how you connect it with that union symbol. Hopefully that's a bit familiar. Practice problems. I'm not going to do a lot of examples yet that are in the book, so you want to take a look at those. Okay, next we will get into 2.3 on functions, defining functions and relations, and 2.4 is on lines, and we keep going. See you next time.